All right, let us get started. Let me introduce myself to you. My name is, as you can see, Syed Hasibul Hassan Chowdhury. We study mathematics here. I'm also in the learning phase. So the main purpose of today's talk is to introduce you to my research, what I am doing currently that I wanted to share with you. The platform was actually built a few years ago when I was looking into certain cases of what I am thinking now, but those were some case-specific situations where which we worked out and published those papers. Now I'm looking forward to a more general framework that will have those specific cases as examples. So that's the goal. So it is related to something called deformation quantization. How many of you are familiar with deformation theory? So just one. So if you are not familiar with deformation, then it will sound a bit exotic. So the practical idea would be to go over something that you are not familiar with. So I will briefly go over the slides, but I really doubt that you would be able to follow it completely. But then I'll go back to my old style of writing on the boards and introduce you to some important ideas that are behind this talk. One of these notions is called quantum groups. Did anyone hear about quantum groups before? Just one, no one else. Or Hopf algebra? Okay. I want you to introduce to this beautiful structure of Hopf algebras. That's my purpose. So a part of our research is involved with Hopf algebra. Okay. So we are looking into this problem from Hopf algebraic perspective that is also related to deformation theory. So that is the reason I want to go over that Hopf algebra part in detail. And the second thing is about certain aspects of symplectic geometry. How many of you did classical mechanics? A lot. Can you say something about Hamiltonian function? All right, so where do we actually do classical mechanics? We do classical mechanics in phase spaces. And what are these phase spaces? Even dimensional smooth manifold, right? That's not enough. We need more structure. What else do we need? Does it need to be Euclidean? Can I do classical mechanics on S2? Can I do it in CP2? Or more exotic stuffs, which are even dimensional manifolds equipped with certain form, which we call symplectic form, that will gives rise to a structure on the algebra of smooth functions on that guy. You are familiar with Poisson bracket, right? So these Poisson bracket, the idea of Poisson bracket is actually inherent in this construction of in this term of symplectic form. So they are interrelated to each other. So Hamiltonian functions are nice functions. It's not just energy function. From the perspective of symplectic geometry, it has a relationship with vector fields on the underlying symplectic manifold. Okay? So to given a function with to a given function, there is a vector field that we call Hamiltonian vector field. So if you have a nice function, which let's call it Hamiltonian function, then the associated vector field is a vector field on that even dimensional symplectic manifold. What do you think that this assignment should respect what? The functions are there on one side on this nice space, which we call phase space in physics. And on the other side, there are these vector fields. What do you want to preserve? Right. So one of my theoretical physics friends long ago said that we are working with Lie algebra. I said, what is the dimension of that vector space? For God's sake, we are not working with vector space, we are working with Lie algebra. Why are you asking about vector space? So on one side, we have the Poisson algebra of functions, which is also a Lie algebra, because the Poisson bracket satisfies all the properties of Lie algebra. And on the other side, there is this Lie algebra of vector fields. So now, I want a homomorphism of algebras, right? Everybody knows what is homomorphism? I hope. It's a structure preserving map. So there is Poisson bracket here. So there are nice functions here, f and g. Their Poisson bracket here. I want them to go to this xf, xg, right? That's the Lie bracket, and that's the Poisson bracket. And now, this is called the Hamiltonian function, and this acts on this like this. Because x of f, x sub f, is an operator that eats a function and spits out another function. So the left-hand side is supposed to be a smooth function, and that smooth function is defined by the Poisson bracket between those two functions. All right. So in our case, we need to start with, so what is our fundamental object? Our fundamental object is going to be a symplectic manifold, which is an even dimensional smooth manifold equipped with a distinguished two form called the symplectic form that will give rise to Poisson bracket between smooth functions on that symplectic manifold. So that's what we want to start with. But well, there was a guy, a Russian guy named Fedosov, Boris Fedosov, who pioneered this idea of deformation quantization. To be more specific, he called it formal deformation quantization. Why formal? Because we don't care about convergence issues. And in contrast to this formal theory, there is this strict deformation quantization pioneered by Rieffel, Mark Rieffel. That's strict deformation, which is very difficult. Why? Because you have these analytical issues arising there about the convergence. But in our case, as Fedosov did, we don't care about convergence for the moment, but we'll also talk about convergence later. For convergence, we will strict ourselves to nice, compact situations where we can address convergence. But for non-compact cases, it's difficult. We can't deal with non-compact cases in the strict formalism. All right. So what did Fedosov did? Fedosov took a symplectic manifold, which is denoted by m omega. M is that even dimensional smooth manifold, and omega is that distinguished form which is called symplectic form, that will give rise to, so that will make this guy Poisson manifold in a certain way. Let's talk about it later. Then, once we have this object, so if you choose two guys from here, F and G, and try to write a product between them, why? Because I want to make it an associative algebra. Everybody knows what an associative algebra is? In which multiplication is associative, right? That's an associative algebra. So how can I write the product of two functions? The straightforward way to write it as a pointwise product, right? F times G is a new function evaluated at x is f of x times g of x. Okay? So those who are theoretical physicists already know that there is this framework of canonical quantization there, where people go to a new space which is called a Hilbert space and represent the functions as nice operators like self-adjoint operators in that separable Hilbert space, right? But you know, those who are proponents of deformation quantization actually don't want to go to that exotic Hilbert space. They want to stay in the classical framework. They want to live in phase space. They don't want to get out of phase space. They want to stay there forever. They find it rather beautiful to stay in phase space. So then, but what is the way out? We want to do quantization, living in the same space without going to Hilbert space, right? How do we deal with that? This pointwise product is deformed. This guy is commutative. F times G is the same as G times F, right? So they invented a way of deformation of this product to make it non-commutative. A new product is born called star product, so that F star G is not the same as G star F. It's a new one. But I cannot do it arbitrarily. I have to follow some, you know, I have to define something following some rules. What are those rules? The rule is the following. So then physicists call it perturbation. You perturbed something, right? They perturbed it. So F star G is the new product, which is a non-commutative product. In some situation, there is a perturbative expansion in some deformation parameter that they denote by h bar, which is the Planck's constant. There are higher order terms there, and when that deformation parameter goes to 0, you exactly recover classical mechanics. Then F star G coincides with F times G, the pointwise commutative product. So there will be higher order terms in this product, star product. So how do you choose that higher order term? So that the linear order in H bar gives you the Poisson bracket. And then there are H bar square terms. Yeah.
So is the reason of choosing H bar only because we want it to go to 0 when we're classifying?
Yeah. So H bar goes to 0, you understand that the quantum effect vanishes and gives you the classical thing, right? But this has to be maintained then. So what is the immediate thing? How can you write G star F is going to be G times F plus H bar over 2, H, this, right? Then subtract one from the other, you get f star g minus g star f to be equal to h bar fg, right? What did I use? The skew symmetry of the Poisson bracket. I think I should introduce this I guy here. Sorry, so there is an I here, and there is this leading order terms. And then I divide. So it's something like that, which physicists call correspondence principle, right? F star g minus g star f. I want the limiting case to be exactly the Poisson bracket. And this is what we are going to call the star commutator. So the observables in the classical world was this guy, the commutative algebra of functions on phase space. The phase space is M, right? That's the classical world of observables. So the quantum world, according to canonical quantization, is the self-adjoint operators on separable Hilbert space, right? Representing the classical functions, right? Associated with each function, you have a self-adjoint operator on that complex separable Hilbert space. So that's canonical quantization, but we don't want to do that. So instead of doing that, we write F as a formal power series. This is a power series. So in general, any observable in the quantum world is going to be something like this. A formal power series in H bar with coefficients belonging to this space, C infinity M. So each of these things, F0, F1, F2, are smooth functions on M. All right? All right. Now, I'm going to introduce you to this non-commutative algebra. So elements here are, so of course it's a non-commutative algebra, it's a vector space, right? So the elements of the vector space, the underlying vector space, are formal power series in H bar with coefficients belonging to that commutative ring of, everybody knows that this is a ring, right? Or ring of functions. So now, if I have, then bilinearly I can write the star product between such elements. So it becomes a non-commutative algebra. So the observables are now power series in this world, obeying a star product, and that star product has to satisfy that correspondence principle. So these are all inspired by physics.
Sir,
Yeah.
again, I'm thinking from a physicist point of view.
Yeah.
So since we are, writing F as a power series like this, but the scales of the terms are not the same.
Right.
If we consider F naught, well, from again physics perspective, it's the classical background, within which we are defining the perturbations in each part.
Right.
So in that case, each term does not scale equally, right? Like F naught is not the same as H bar F naught when we're dealing with the whole.
Right. They're different coefficients. The coefficients are different. They could be, they could be any function because you don't address convergence. So anything is good as long as they belong to this ring of smooth functions on M. Yeah. Yeah, exactly. Yeah. you can focus on correlation functions. That will, encode a lot of things, a lot of information. All right. So this is our quantum world. Okay. In the language of deformation quantization, this is the quantum world, and you have a preferred star product between elements of it, right? That is the multiplication of algebra. All right, to understand it a little more geometrically, we want the objects here to be sections of certain bundles. And these adds the flavor of geometry here. So I'm going to explain that to you very easily in very down-to-earth language without going into detail, but that will leave me with not going into the detail of what I am planning, what I am currently doing, because I think these are more involved. Okay, I think, all right, so there is one more thing. So you more or less understand what was the program of Fedosov. He was starting with this commutative algebra of smooth functions on a symplectic manifold, and there was a deformation of the observables, and he used the, constructed the quantum world. Okay, but I did not tell you that these things here have more geometric properties, as they are, to be more precise, flat sections of some bundle. I did not construct that bundle yet. It's not actually a vector bundle. It is an algebra bundle where the fibers are infinite dimensional associative algebras. Okay? I'm here to talk about that thing, that geometric part. But apart from that, the Fedosov thing is complete. But what is new in our case? In our case, the new thing is that we want to do the same thing as Fedosov is doing here in this world of symplectic manifolds. But our symplectic manifolds are special symplectic manifolds, which are called coadjoint orbits. Okay? What are coadjoint orbits? You need to understand. I want to, brush your Lie group, Lie algebra memories. I hope you are all familiar with these things. Given a Lie group, G, it's Lie algebra, calligraphic G, and the vector space dual to this Lie algebra. It's not dual of the Lie algebra as a Lie algebra. It's the dual of the Lie algebra as a vector space. That's G star. So these are the data. And now, so these part, so that was Kirillov, that was Fedosov. Now comes Kirillov. He's also Russian. He was Russian. He's no longer alive. His son is alive. His son's book you are all familiar with. You study Lie algebra from Kirillov, Junior's book. Okay, so no, Kirillov is alive. He's hale and hearty, I guess. He's in Stony Brook, I guess. I'm sorry. So Kirillov is alive. But Kirillov Senior is also alive. He may be very old, but he's alive. All right. So now the focus will be in this dual vector space, which is G star, something like a vector space, but maybe a big vector space. G star, so depending on G star could be odd dimensional, right? If the Lie algebra is three-dimensional, then G star is also three-dimensional. That could be odd dimensional, but G star is endowed with the Poisson structure. You can write Poisson bracket between functions on G star. Okay? But G star is not even dimensional, right? Like we see, it can vary from case to case. They could be different. But now, I want to write an action of the group on this dual. Let me explain how I'm going to write it. I'm going to call it add action, add star. Okay. So add star is the action of this group element G on the dual of that Lie algebra. Okay. So what is it supposed to give you? Another element here, right? G star, another element. So now, if I take the dual pairing of this with a Lie algebra element, so let me tell you where these things are. G is in G, Y is in G star, and X is in G. And this is the dual pairing. What is it supposed to be? A complex number, say. And how is this complex number defined? I'm defining this coadjoint action, and this is supposed to be Y, the adjoint action of the group on the Lie algebra. We know this. Are you familiar with the adjoint action of the Lie group on the Lie algebra? By conjugation, right? Gx G inverse. Gx G inverse. So Y, I think, yeah, G inverse Xg, whatever. Inverse does not matter. So this is how you define this action, which is called coadjoint action. So now if I choose a point in my dual of the Lie algebra, and then I vary these group elements, all the group elements in the group, I get something which is called an orbit. So something like this, an orbit. By varying group element, you get an orbit. Such an orbit is called coadjoint orbit. And coadjoint orbit are nice phase spaces. These are all even dimensional phase spaces. Even dimensional spaces which are phase spaces. So now the geometry tells us that G star, yeah. Yeah. Which one is manifold? G star? Yeah. So it's a dual of the Lie algebra, which is a vector space, and it is trivially a manifold. It's vector space, so it is trivially a manifold. Now the point is that these things, these are called leaves of foliation, or to be more precise, symplectic leaves of foliation. So they stack onto each other to form the whole G star. So G star itself is not a phase space, but inside which are foliated phase spaces, foliating phase spaces which foliate the whole G star. Yeah.
How do we keep the orbits again? We just vary the G or
Yeah.
like and keep the y-axis same? Or
No, so suppose you are looking at this O lambda, the orbit, by definition. So people write it with a star to denote that it's coadjoint orbit. So it's the collection. So it's add G star lambda as G varies in G. That's the definition. Okay? Is the definition clear to everyone? And these are either they coincide on each other or they disjoin. There is no non-trivial intersection between them. Nice things, right? So for example, we can take the case of a Heisenberg group. Heisenberg group. What is Heisenberg group? What is the Lie algebra? Heisenberg algebra is R3, whose dual is R3. R3 is a Lie Poisson manifold, but not symplectic. Why? Because it's odd dimensional, but it is foliated by two-dimensional R2 spaces. Those R2s are precisely the coadjoint orbits of the Heisenberg group. For non-zero values of z coordinate. For 0 value of z coordinate, the coadjoint orbits are 0-dimensional degenerate points. So, there are two types of coadjoint orbits for the case of Heisenberg group, either 2-dimensional or 0-dimensional. 0-dimensionals are degenerate orbits, 2-dimensionals are non-degenerate orbits. And if you delve further into this, you will see that the z coordinates are actually 1 over h bar. They are in correspondence with the unitary dual of the Heisenberg. The h bar actually comes from the unitary dual of the Heisenberg. So, that is my motivation of connecting Fedosov with Kirillov. I want to tie up that deformation parameter h bar with the unitary dual of a group. That is, so I don't know, not here. Maybe in the Facebook announcement, there is this word unitary dual tuned. The unitary dual. By the way, what is unitary dual of a Lie group? I'm sorry that there are too many terminologies, but if you start exploring them, eventually you will learn all of them. What is unitary dual? So, even in theoretical physics, people are interested in fundamental objects, right? Wigner's paper, have you read, all of you? Irreducible representations of inhomogeneous Lorentz group. That's one of the most fundamental, podium of theoretical physics, right? Which classifies all possible fundamental, particles, which are represented by a class of an equivalence class of irreducible representations of this inhomogeneous Lorentz group. So, okay. So, when we are saying that there is a class, meaning that there are many elements in that class, it's an equivalence class. And how can I go from one representative to the other representative? By a unitary transformations. We say that they are unitarily equivalent. Okay? But if you take two distinct classes, you can never find a unitary representation transforming one into the other. They are totally different. Okay? So, now the point is that you have these coadjoint orbits on one side, and representations are reminiscent of what? Quantum mechanics, because you go to a Hilbert space, right? You represent your group elements as unitary operators on some separable Hilbert space, right? So, representations, when representations come, you are in quantum world, okay? So, now what Kirillov showed that when your underlying group is nilpotent or some solvable exponential, solvable plus exponential, nilpotent are always exponential, globally exponential, but solvable may not be exponential, but if you tie yourself to the situation when you have solvable and exponential, probably in that case, I don't remember exactly if it's if for solvable exponential Kirillov's theorem would work, but I can answer that later. I don't remember it exactly, but for nilpotent it always does. So, on one side you have these coadjoint orbits, and on the other side you have the unitary dual of G, which are equivalence classes of irreducible representations of the group. And Kirillov showed that there is a one-to-one correspondence between them. Associated with each equivalence class here, you have a phase space here. There is a one-to-one mapping. But it's not possible everywhere. For any Lie group, you cannot say that. Okay? For a Heisenberg group, you can say that. And that is the reason for each value of h bar, you have a representation, an irreducible representation of Heisenberg group. But then you can ask me, why do we have Stone-von-Neumann theorem, which tells us that there is only one representation? Because from physics point of view, you have frozen the h bar axis. That is the reason you have only one class left with. But mathematically, nothing prevents us from taking other values of h bar. We have infinite freedom, we mathematicians, right? We are not bound with the physical reality. We can, whatever we choose, we can do whatever we like, okay? So we vary h bar, we get different irreducible representation of the Heisenberg group, okay? All right. Now, our case is, I told you that Fedosov worked with this m omega. We are going to work with O lambda 0 omega kks. Kks is Kirillov constant Suryaev form. It's after those three mathematicians, Kirillov, constant, Suryaev. KKS2 form, and our symplectic manifolds are those coadjoint orbits. All right? Yeah. Yeah. Between the unitary dual of the underlying Lie group, G hat, and the phase spaces there, the coadjoint orbits. Yeah. That's the infinite dimensional. G hat is a very wild space. It's not easy to deal with. G hat may not have a manifold structure at all. G hat is a very badly behaved space, but it is widely studied in non-commutative geometry because the worst spaces are most respected in non-commutative geometry. Okay. So this is the rationale. This is what we are going to do. We are going to, blend Kirillov with Fedosov. All right. So let's go on to the slides now. Slides. Oh, I'm good. All right. So this is orbit. Orbit method is the one designed by Kirillov. So the name of the book is Method of Orbits. It's available everywhere. You can study it from there. So the method of orbits it's a very beautiful mechanism to find unitary irreducible representations of certain classes of groups. Very easy. And what comes for free? The geometry comes for free. You have this beautiful geometric view as well there. All right. And secondly, you have Fedosov there, but h bar. So h bar is a single parameter, right? So I'm saying that this is the case of our Kirillov case for Heisenberg group, right? I said already that the deformation parameter comes from where? The unitary dual. For the Heisenberg group, the unitary dual is labeled by h bar. So they two actually coincide, not exactly coincide, because the coadjoint orbit of Heisenberg groups are what? Two-dimensional Euclidean spaces, which are flat. But say we take SU2 that Kibria is working on. SU2, what are the coadjoint orbits? It's again R3, the dual. The dual of the Lie algebra is again R3. But that is not now foliated by two-dimensional planes. It is now foliated by concentric spheres. So the coadjoint orbits are S2, one after another. Okay. So obviously, your quantization on two-dimensional plane is not going to agree with the quantization on S2. That would not make any sense, right? So they are actually different. So I cannot say that whenever I have single parameter, I always have Heisenberg. Or I cannot say, because for SU2 I still have one. So what is the parameter there for the SU2 case? The radial direction is the parameter, the transverse direction, transverse to the two-dimensional spheres. So that is the idea. So when you look at the foliation of G star into the orbits, you see these stacks of planes or stacks of spheres, right? And you are quantizing them. And what is your parameter? The deformation parameter is the transversal direction is going to be your deformation. So that's our theory. So you can have situations where there are more room in the transverse direction, right? Suppose you have 7-dimensional dual Lie algebra and your coadjoint orbits are 2-dimensional. Then you have 5 degrees of freedom. So you can use 5 parameters to quantize your coadjoint orbit. So depending on that, we have a richer situation. We have multiparameter deformation quantization. Okay? So our idea is to deal with multiparameter deformation quantization, what Fedosov did was just a single parameter formal case. But now it's not just a formal parameter H bar. It is endowed with a structure, the unitary dual that Neon was saying. It is a very badly behaved space, but we have structure there as well. We have mathematics to deal with that space that we do in harmonic analysis and what is it called, in non-permitted geometry as well. All right, so new idea is that I have when n is 1, I have the Heisenberg case or SU2 case. These are the situation, but in general we can have. So these big N is the room, the number of transverse parameters. So let me say a little more about this. How many of you are familiar with orbit stabilizer theory? Have you studied it in Lie group? All right. So here there are these orbits, okay? The orbits. So if you have the Lie group G and you fix a point lambda 0 in the dual of the Lie algebra, then there is the coadjoint action of the group on the Lie algebra, on the dual of the Lie algebra, and you have a stabilizer group under that action. So this quotient is not necessarily a group, everybody knows, right? But I can always take the left cosets there. That is a manifold, but that is not a Lie group. When will that be a Lie group? When the subgroup is normal, right? But it is not natural. This is not in general normal. So this is isomorphic to the orbit. And so then you can go to the Lie algebra version and write it in the Lie algebra version, write it like this. Oh, sorry. That's the Lie algebra version. That's a vector space, is the tangent space to that orbit. So this immediately tells us how many degrees of freedom in there in the transverse coordinates. suppose your Lie algebra is n plus 2n plus s dimensional, and your orbit is 2m dimensional. The orbit is even dimensional, 2m. So the transversal directions is 2n plus m minus 2m. So that's my n. That is that n. That many degrees of freedom you have in the transversal directions. Okay? All right. Now the goal. Build a multiparameter. Now I cannot just avoid it anymore. I have to go to the geometry now, the construction of that bundle that I talked about. So enough algebra is done, but now geometry needs to be done. So where is it happening? Everybody studies GR. Where does it happen? Where does GR happen? Tangent bundle on the space time, right? Your Levi-Civita connection, whatever you do, you take sections of this tangent bundle on space time. So what are sections of tangent bundle? Why are vector fields important? Because these are vector fields, right? Sections of tangent bundles are vector fields. Now, so what is the space of vector fields on a given manifold? Does it have the structure of a Lie algebra? It does. It's an infinite dimensional Lie algebra. But you know, I have encountered many people who think that Lie algebra is always finite dimensional because it's the tangent space to the Lie group. But that's not the idea, right? Yeah. So Lie algebra does not have to come from a Lie group. It can arise very independently without reference to any Lie group at all. But associated with each Lie group, you have a Lie algebra. That is isomorphic to the tangent space at the identity. Okay? So the more general Lie algebra associated with a smooth manifold, the Lie algebra of vector fields, which I just said that is infinite dimensional, inside which is a finite dimensional interesting subalgebra, which is the, of course, Cartan subalgebra is also interesting, yeah, because we study isotropy with the Cartan subalgebra. But when my smooth manifold is a Lie group, okay, then I have a G action on the manifold, right? Because my Lie group is also equipped with the structure of a group, so that I have a well-defined action of the group on the manifold, and I can talk about left invariant vector fields. The vector fields which are invariant under the left action of the group on itself. So these subalgebra of left invariant vector fields is isomorphic to the tangent space at identity, which is the Lie algebra of the Lie group. So here comes this finite dimensional Lie algebra of a Lie group, but Lie algebra in general can come very independently. Okay? And in fact, after a linear algebra course, I suggest that everybody should study Lie algebra even before studying Lie group. Study Lie algebra independently. Okay, so what I was saying was at this bundle, right? So I was talking about GR. It happens on the tangent bundle. But now, how does so this intuitive notion of vector bundle comes into play when I have a base manifold, and each point, intuitively speaking, very roughly, at each point you attach a fiber. Each fiber is a vector space. You glue them together, take the disjoint union, you call it a vector bundle. Then you can talk about sections of vector bundle, okay, where each fiber is a vector space. Now, so when you talk about vector bundle, you have to mention what your base manifold is, right? base manifold. Your space time is the base manifold when you are doing GR, right? So, our base manifold is that coadjoint orbit O lambda 0, which is the symplectic manifold we started with, right? And now, there are fibers there. From our GR knowledge, we know that these fibers are tangent spaces, right? Tx O lambda 0. I take its dual, which is the cotangent space, which are relevant in classical mechanics, right? Because Hamiltonian formulation works in cotangent bundle. So, I take the cotangent space. Okay? Then I take the symmetric algebra of this vector space. How does it look like? It's a polynomial algebra. Symmetric why? Yeah, you can think of it as a polynomial algebra, so you can switch the coordinates. Okay? Take the linear combination. It's an infinite dimensional vector space. And then take its tensor product with this. So, I'll explain the meaning. So, if you don't understand, don't get frightened. So, this lambda is actually multiparameter lambda 1, lambda n. So, it means that I have a formal power series of elements. Formal power series in how many coordinates? N coordinates, big N, lambda 1 up to lambda n. That many coordinates, formal power series, and the coefficients are these guys. Okay? So, if I have something like f0 plus f1 lambda 1 square lambda 2 plus f2 lambda 1 cube lambda n, can be something anything like this. So, these coefficients should come from here. Okay. Now, this is an infinite dimensional vector space. So, each fiber is this infinite dimensional vector space. So, for each point, you have something which you call W of x. You take the disjoint union of all this x in where? O lambda 0, right? Which we call W. I have given it a name. I called it G lambda bundle. It's something that I called it. It's a new thing. This object is G lambda bundle, according to me. So, lambda is a multiparameter guy, and G is denoting the fact that we are in that Lie algebra framework. Now, the interesting part that Kibria should do it, that one can actually start with, so O lambda 0 is a symplectic manifold. Of course, it's a coadjoint orbit and hence a symplectic manifold. And everyone knows what a symplectic connection is. You can study it alongside GR. So, in GR you have G, that metric, here you have omega. You can do pretty much similar things in symplectic geometry as well. Okay? Whatever you do there with G, now you do with omega. You find Christoffel symbol, you find curvature tensor, you can do everything. So, that is what Fedossov did. So, there is a connection, but apart from Levi-Civita connection, this is not unique. The symplectic connection is not unique, whereas Levi-Civita is unique. So, this connection I denoted by nabla. Nabla is that connection. And there is, so the fibers, there is an operator in that fiber that acts on a section in general and reduce the degree of y by 1, right, and increase the degree of the base form by by taking a wedge in that direction. So it's a fiber coordinate and gives a new base form. Okay. So these are these two operators, nabla, which is a symplectic connection, this is delta. And when you do it for coadjoint orbits, you can see that. So you have a connection. So if you study differential geometry at the, well enough, you'll see that the curvature is square of this guy. So the curvature is d square, right? So d square, by using certain algebraic property, you can show that this is non-zero. It's not zero. It doesn't turn out to be zero. It has to deal with the curvature of the curvature called Fedosov curvature with of the underlying bundle. So this is not flat because the curvature is non-zero. So the idea is to make it flat iteratively. So in step by step, we slice out and make it flatter, 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 and finally it's flat. This is this thing. This is a very beautiful iterative process by means of which you can make it flat. All right. And you see that for Fedosov case, you did not have this something, but in our case, we have this new something because we are dealing with multiparameter guy. And what Kibria did a few days ago, he showed that our formalism collapses to Fedosov's formalism for the special case of single parameter case. He proved it. Okay. So in the recursive situation, so let me go to the next slide. This way, right? No. Like I said, that these are the fibers of these fiber algebras, and you take the disjoint union of these fiber algebras and construct this algebra bundle. There is some grading thing associated, but don't delve much into this degree thing. You can do it later, but let's try to have this. So this is the operator that acts fiber. What I said that it it differentiates the y coordinates once, so that you have one less degree in the y coordinates and wedge it with. So this notation tells us that in a compactified way. And there is delta inverse. It's invertible. This is the contraction along that vector field. Okay. Everyone knows that what contraction is. It's the opposite of wedging. It contracts. It reduces the degree by 1. Okay.
Sir, why is it necessary for this to be flat?
No, it does not have to be flat. Which flat? Oh, curvature. It's because even in gauge theory, we are interested in flat connection. Flat is a very, very beautiful thing. All right. So the idea is to make it flat connection. In theoretical physics, we are also interested in flat connections. Flat connections has very all right. So once you have these things into play, what you can show following, Kibia should do it for the multiparameter case as well, that the space of flat connections. So if you take a section of this bundle W, the disjoint union of all these fibers, and then apply this D, it should result in 0. So such sections, the set of such sections is called the set of flat sections. And you can show that the set of flat sections is now isomorphic to this guy that we started with. Is the geometry clear to everyone now? These are precisely the elements of what we started with. So this is the set of flat sections under Fedosov connection of the G lambda bundle that we constructed. Okay? All right. Then this is the iterative process. So what Kibria did is Kibria proved that these things, these iterations actually converge to something finite. And that thing is this R, Ri, right? That's the final term R. We have to prove that it is convergent, right? Otherwise, we cannot do it. So prove that it's convergent, and then this makes sense then, Ri. For each I, Ri makes sense. And so this is a recursive process. So now what Kibria is doing is to explore this thing for the case of SU2 in detail. And now we should be able to understand that we have this bundle and we have the algebra of flat sections. Now you can descend to functions on the coadjoint orbits and you can lift it to the sections of the bundle as well. And you can descend to the, so the idea is that the sections will be a power series whose leading order term should coincide with that function thing. So the function thing was there in the beginning. And then when you lift it to the section, to an appropriate section, it becomes a power series. So the leading order term captures the classical flavor. Okay? All right. And then I think we should not go into these things, but let me just very briefly tell you what we are doing there. I told you that classically we had this dual of the Lie algebra and we have a foliation of coadjoint orbits, right? And you quantize each coadjoint orbit. So now you take the family of quantizations together. Now transversally you can go from one quantization to another quantization. And the idea is to compare these family of quantizations. My idea is to construct appropriate Dirac operator, appropriate elliptic operator, and study its index and see if there is a jump in the index. And if there is a significant jump in the index, you conclude that there is this huge variation in quantization. So something along the way, Boris Segan and Nest, I forgot the name, his name. The last name is Nest. Nest and Segan together studies in a very seminal paper published in Advances in Mathematics in the 90s probably. So that is the thing, okay? So this is the topological invariance index, K-theory, cyclic homology. By studying those things, one can explore if these quantities, you can compare this family of quantizations. For the SU2 case, I have this Dolbeault operator, and we saw that, the quantizations are almost similar because they are all two-dimensional spheres, right? So it is expected to stay the same, the index of the operator, and it does actually. But when you have, for the case of the supersymmetric quantum mechanics that we studied with Jim a year ago, there we studied a nilpotent Lie group, and there is a reduction, huge reduction from of coadjoint orbits from R4 to R2. So it would be interesting to study this thing there. So when we go across that elliptic cone-shaped surface, I think there will be a jump in the index of the operator. So these are yet to be studied, okay. But let's move on. This part just forget. But you understand what I mean there is, in the transversal direction you construct a path. So Nian could be interested because your MSc thesis was doing something like this. Okay, and this part also, I think this has to deal with polarization subalgebra, geometric quantization. These are heavy stuff. So, you know, you are also tired, I am tired too. Let us not move into these things, okay? And this is the deformation theory I tried to explore using O-operator theory, and some interesting things come up that Mashrafi is trying to explore by studying differential graded Lie algebra and all these things. But again, these things are also technical. Let me not delve into these things. But what I want to say finally, that the Hopf algebra structure that I don't know if I have added it here. I don't think I have added it here. No, I don't think I have. So the Hopf algebra structure that I wanted to talk to you about. So I think I will finish it with. We don't have much time, right? Yeah. All right. When did we start? At 5, right? Yeah. Okay. So yeah. So I will not. I'll try to be as brief as possible. So, like I said in the beginning, that I want to say a few, spare a few words about this Hopf algebra thing. You should all know, especially the theoretical physicists, about quantum groups. Okay. So there is a relative notion called universal enveloping algebra. Which we denote by U of G of a Lie algebra. You have a Lie algebra, say. You can construct a universal enveloping algebra of that Lie algebra. Does everyone know that Lie algebra is non-associative? Because you have the Jacobi identity and all that. It's non-associative. It's not associative. So if you have X, you have Y, two Lie algebra elements, it does not make sense to talk about X times Y, right? There is nothing like X times Y in Lie algebra. You have bracket of X and Y. That's the algebra operation there. So in Lie algebra, you have the bracket of X and Y. But there is this notion of, given a vector space over a field F, one can define the tensor algebra on that vector space, given by that the ground field directs some V directs some V tensor V and goes on like this forever. It's called the tensor algebra associated with that vector space. Okay. So V is a, let's say, take V to be a finite dimensional vector space over the ground field K, then one can construct this. Now tell me that this, so I have to define the algebra operation here. I called it a tensor algebra. So what is the operation? So if I take V1, Vm and the multiplication of W1, Wn is equal to V1, Vm is called concatenation. You just bring them together and put a tensor product in between. That's the algebra operation. With respect to this algebra operation, it becomes an associative algebra now. Okay? But I am saying that it's a universal enveloping algebra of the Lie algebra. I can always choose the vector space to be G. There is no harm in that, because G is also a vector space. You understand it, unlike my theoretical physicist friend, I hope, who asked me not to study Lie algebra as a vector space. But so once you have this vector space G, then you can form the tensor algebra of this vector space, right? But does it contain the flavor of the Lie algebra? It does not, because it treats G as a vector space. So, it does not contain. So, I take this tensor algebra and quotient it out by a two-sided ideal generated by the following elements: x tensor y minus y tensor x minus the commutator, the Lie bracket of x and y. All such elements which form the two-sided ideal of that tensor algebra, and then mod it out, and then okay. So, now tell me one thing, that I have x cross y cross z minus x cross z cross y, which is in G3, right? By G3, I mean that this, you can write it Tg as G tensor n equal to 0 to infinity. So, that is G tensor 3, right? That is there, but on the other hand, you have this, right? They belong to the same class here. Yeah. Because I have modded it out by this. But they are different objects in T of G. But in that quotient space, they belong to the same class. In Tg, it is in G2. They are different, but I have modded it out, and this is called U of G. Okay, to be more precise, so if I take x, what is this product? Right, according to the definition. And what is y dot x? What is x dot y minus y dot x? And it is supposed to be what? In U of G, the universal enveloping algebra. Now, my tensor algebra, while modded out by that two-sided ideal, has the flavor of the Lie algebra. So, what are you the আমাদের কাছে একটা non-associative algebra আছে, which is a Lie algebra. Now, I don't like to be in this world. I don't like non-associativity. I want associative world. কিন্তু ওখানে তো আমি ইচ্ছা করলেই কিছু ওখানকার সব কিছুকে দিকে একে দিয়ে রিপ্লেস করতে পারো। So, I want the best possible fit there that is going to represent this guy there. That is that universal enveloping algebra, which keeps the flavor of, it best represents that guy, the non-associative. But still, what is such an example in geometry? You know the spaces that are not simply connected. So, you take the universal covering map. Suppose you have, so those who do theoretical physics are all familiar with SO3, which is not simply connected, because you go there, the antipode will go there. You can never shrink it to a point. So, it's not simply connected, SO3. But you need something which is simply connected, which best captures this SO3, which is what? SU2. You have the Lorentz group. For when you study Wigner's paper, you have what is it called? SO13, the Lorentz group, right? Which is not simply connected. But you study SL2C instead of SO13. That's the universal covering group. But we have to remember that we have to take that representative that best encapsulates the structure, which keeps the flavor intact. So that's our U of G, universal enveloping algebra. Now, I'm not going into the detail. These are all written down here. I wrote it up because I wanted to, tell you about these stories of Hopf algebra. So in a given vector space, you can tie the algebra structure with its dual structure, which is called coalgebra, in a compatible way. In a compatible way. When I say a compatible way, a lot of commutative diagrams are underway. So in a compatible way, I have coalgebra married to algebra structure. Okay? So, and then I call it a bialgebra. Such a thing is called a bialgebra. Then I add another structure to it, which is called antipode. Antipode is like the group inverse thing. And together, they form a Hopf algebra. Okay. So you understand that there is an algebraic structure and a coalgebra structure there. So your U of G, the universal enveloping algebra, can be seen to be a non-commutative but co-commutative Hopf algebra. Its co-product is, in a certain sense, commutes. There is a flip operator under which it remains the same. Okay? It's co-commutative. So what, people started thinking about, can we deform this structure? And Jimbo, Miwa, and what is Greenfeld, these people found out a way. They have a unique way of deforming the co-product, keeping the product structure intact. They deform the Hopf algebra structure. It's called the deformed Hopf algebra. So now I can go back and ask that so you have this non-commutative, co-commutative Hopf algebra, and you have this universal enveloping algebra. And suppose that universal enveloping, that Lie algebra is associated with the Lie group. So you can trace back to that Lie group from U of G. Now my question is, after the deformation, once I have a non-commutative, non-co-commutative Hopf algebra, what is the associated group? That group is called the quantum group. I don't know. It does not have anything to do with quantum mechanics. Perhaps it has, but I am not familiar with. But it's called quantum group. So if you think that quantum group has to do with quantum mechanics, then you are mistaken. It has to deal with Hopf algebra. I don't want to bore you anymore, but this is what I could do. But you have a sort of idea what I'm working on, at least. I've been able to give. But there are many other sides of this project. We are still working on them. But I'm sorry that I could not go over all of them. It requires some background, probably. But I have a wonderful, I should not say that it's wonderful, but I believe that it's a long enough proposal written. I can share it with you. Kibriya has it, the updated version that you can have a look. We are all looking into it and trying to see if we can accomplish these things, these tasks. Okay, that's all for today.